Hello everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In this class, we will study about the DC biasing of JFET and today we will discuss the fixed bias of junction field effect transistor which is N channel. So this is N channel JFET and we are discussing the fixed biasing technique of JFET. So here we can see that arrow is pointing towards the device. So it is N channel. We know that in N channel the arrow is always towards the terminal. Here we can see that we have input signal V in and output signal V out. These two are AC signals in nature. Okay. And these two C1 and C2 are coupling capacitor which is used for rectification process of AC signal. Here we can see that a resistance RG is connected with gate terminal and resistance RD is connected with drain terminal. Here the source terminal is grounded and we have two biasing batteries. One is VGG and second one is VDD. We can see that VGG is connected in this manner, so it is reverse biasing the gate. So this is our negative terminal and this is our positive terminal. It is reverse biasing the gate terminal. Now we can see that here, if we have to do the fixed bias analysis, we will process the DC analysis over there. And we know that in DC analysis, the AC signal we assume 0. So V in or V naught, we assume they are 0. Okay, they both are 0. And also the C1 and C2 are removed or we can say they are open circuited. Open circuit. Why so? Because we know that XC reactance, capacitive reactance is 1 upon 2 pi FC and frequency of DC signal is our 0. So XC will become infinite. So infinite resistance, infinite capacitive value means it is open circuited. Okay, so we have to remove C1, C2 and we have to make V in and V out 0. So we will have to make an equivalent diagram for DC analysis of this fixed bias circuit. So this is the equivalent circuit of N-channel JFET in fixed bias configuration and we are doing the DC analysis of that. We know that this is our VDD, this is the resistance RD and current will always flow in this direction from drain to source in N-channel JFET. Here we can see that this is negative potential, this is positive and this is our VGG biasing battery and a resistance connected with gate and we know that the current IG which we consider as 0 in case of JFETs. Why so? Because the input impedance is very high. Input impedance of JFET devices is very high. So we can neglect this IG also. So IG is almost 0. So we can replace this resistor RG also. Why so? Because no voltage drop across this resistor we will found. So if we have to do the KVL analysis over there, we don't have any voltage drop across this resistor. So we can easily remove that. Okay, we can easily remove that. So we will join this line as like that. So this is our circuit for fixed bias configuration of JFET. Clear? This is our VGS, gate to source voltage. This is positive terminal and towards the source is a negative terminal. Source is grounded. This is negative terminal. This is our VDS and this is positive terminal. So this is the equivalent circuit diagram for N-channel JFET in fixed bias configuration. Now what we have to do, we know that in DC analysis, we need 2 points. So we can find our 2 points. So one we need ID which is in vertical direction or in Y coordinate of this system and in X coordinate we have VDS which is drain to source voltage. So ID in vertical or Y parameter or VDS in X or X coordinate in horizontal parameter. Okay. Now we can see that we have to apply KVL in this loop. Okay. If we apply KVL in this loop, input loop we can say. If we apply KVL in input loop, what we will get? We will get like this. If we apply KVL in input loop, okay, KVL in input loop. So if we apply KVL in input loop, we know that this is VGS plus minus if we are traveling here and there. So this is plus VGS. This negative and this positive negative. So plus VGG. No other voltage in this loop. So is equal to 0. So we can see that VGS equal to minus VGG. So this is our first equation. Okay. VGS equal to minus VGG. Now here, the second we will apply KVL in our output loop. Okay. So in output loop, KVL in output loop. Okay. So KVL in output loop, what we will get? We will get a voltage VDD. So here the voltage VDD uh, is equal to, here the voltage drop across this resistor is VD, which is nothing but ID into RD, ID into RD, plus here this voltage plus minus VD. Okay. So here we have VDD equal to IDRD plus VDS. Now here we can see that this ID we have to calculate. Okay. We know that RD is somehow fixed. Drain to source voltage is also fixed. VDD is fixed in nature. We have to find this ID so that these two equations we can put directly on the VI characteristic for finding for DC analysis. Okay. Now here we can see that ID we can find in JFET from Shockley equation. In our transconductance also, transfer characteristic of JFET, I already solved the equation for that ID current, drain current, and we use the Shockley current equation. So here we will apply that. So according to Shockley equation, what is ID? I am writing here. Okay. ID is nothing but IDSS 1 minus VGS upon VP whole square. Okay. So this current we already discussed in our transconductance topic. You can check on that, and we use this standard equation to find the ID current. So here ID, we have IDSS 1 minus VGS is nothing but minus VGG. So we directly put that. So it will become positive VGG upon VP whole square. One thing I have to consider here, that IDSS is drain source saturation current, and we already discussed in a transconductance topic. The value of that is given in a particular, if numerical can, then it is given, or otherwise it is standard value. Now here 1 plus VGG, VGGs are fixed quantity because it is fixed bias. So we are fixing the two batteries, DC batteries are fixed, VDD and VGG are fixed. So we know the value of VGG. VP is our pinch off voltage, we know the value of VP also. So these all quantities we know, and after putting all these, we will get the value of ID here. Okay. So ID is whatever the values coming here is the value of ID. So now we have VGS, which is nothing but minus VGG. We put the value of VGS here so that we will find the ID. So we have ID now. We have VDS now. So VDS is nothing but what? VDS is here VDD minus IDRD equal to VDS. Okay. From this equation, what is VDS is nothing but VDD minus IDRD. Okay. VDD is here minus IDRD. So these two, from these two equations, we directly put them on this curve and we will get the Q point from that. Okay. So VDS is nothing but VDD minus IDRD, somewhere it is, let's suppose somewhere in between like that. So this is our Q point. Okay. IDQ and VDQ. From where we are getting this? We are getting this VDS is equal to VDD minus IDRD. ID from where we are getting? We are getting the value of ID from this equation. Okay. And ID we will directly put here. So we will get a particular DC analysis point, which is nothing but the Q point here. So this is the whole process of what a fixed bias JFET is doing. Now in another class, we will do another type of biasing techniques. Till now, thank you so much.